All right. Hello, everyone. Welcome to today's Physics Meets ML. It is a pleasure to have Eva Silverstein from Stanford here. She is going to tell us about early universe models as optimization algorithms. Probably many of you have already realized it, but there's energy landscapes all over the natural sciences with many metastable minima, whether we're talking about deep learning loss landscapes or in cosmology, having many metastable states, many metastable vacua, which is something that arises in string theory, or protein folding or spin glasses. What she's going to propose to do here is to take some of the ideas that have come out of string theory as applied to cosmology and tell you about how you can use them as optimization algorithms for neural networks. So Eva, it's wonderful to have you here, and please take it away. And please also feel free to ask questions throughout, everyone.
Yeah, well, thank you very much, Jim, and everybody for the invitation. This is a very fun development in collaboration with Bruno De Luca, who's I think also on the call. We have one paper out on this, and we're building from that, particularly on the experimental side, but both that and the theory of it. And I want to say this is also has benefited from discussions with many people at this interface of physics and machine learning, as indicated here and beyond. So, okay, as Jim already nicely introduced, for many problems, we have some sort of loss function. We'll use physicsy language and call this V for often notation for potential energy. And we wanted to send this, and it's typically non-convex. So of course, everybody in this field is familiar with that in the context of machine learning and more general data analysis. There's another application that I find people aren't always aware of that one can have in mind, which we will also attack, which is the problem of solving PDEs. Of course, numerical methods for solving differential equations go way back, and there are many methods that work for various problems. But this is a new, using machine learning ideas or neural networks for that is a relatively new and possibly underdeveloped area. So partial differential equations occur all over science, and so it's a great target. And here I'll say a little bit more about this, but the basic idea is to take the loss function then to be the sum of the squares of the equations you're trying to solve. So if you get to the bottom of the loss function, you've solved the equations. That includes any boundary conditions for the equations. And here there's a, if a solution exists, then that is one or more global minima of the loss in that case that you're after. Okay, so of course we all know that gradient descent has been part of, and its variants, many modern tweaks of it has been very successful as part of the revolution in deep learning. But it's a little hard to predict. It sometimes gets stuck. There's nothing about it that guarantees that it won't. And also there's intuition in the stochastic case that it should sample among different solutions, for example, in PDEs where that's of great interest. But it's sort of hard to tell if it will or if it won't. And one of the benefits of the very different approach that we'll take here today is that we'll have another property of the optimization algorithm that in physics language is, believe it or not, energy conservation, even though what we want to do is descend to the bottom and stop there. And that energy conservation in this framework will lead to greater calculability, in particular things like a formula for distribution of results over all the solutions of the problem. And in contrast to gradient descent, which is friction-based or friction-dominated in physics language, in this case, we can have zero friction. And so just to anticipate a little bit, the prototype for this will be an algorithm based on physics dynamics in which it's relativistic, but where the relativistic speed limit depends on the loss itself. And so you don't need friction, but the algorithm will stop when it gets and slow down very, very dramatically as it gets toward the bottom of the loss landscape. That raises an obvious question of what is special about v equals 0, which we can talk about, but it's often not an issue, and in particular in the loss being the PDE squareds and so on in this problem. And also, it turns out in kind of the small scale benchmark machine learning problems like CFAR and MNIST and so on, it hasn't, this dependence on V itself has not been much of a problem, but this is something that we should discuss. So this is kind of the brief teaser for the idea, and I'm going to spell it out, bring in the physics context for where this idea came from, and share with you our theoretical calculations and experimental verification throughout the talk. So there is one paper that we saw that was somewhat similar, but not really the same, which is a very interesting paper called Relativistic Gradient Descent, where they also used a relativistic theory of the motion on the loss landscape. But there they still had friction. They contracted the phase space with a frictional term rather than preserving energy conservation, dispensing with the friction, and having the relativistic speed limit depend on the loss, which is what we're going to do. Okay, if that was a little bit cryptic, don't worry, I'm going to explain this idea at length in the talk. And please do discuss all along the way. Okay, so for those for whom this is news, let me just give a schematic, a little bit more of a schematic of the business of PDE solving using neural nets. There are many, many papers on this. One of the earlier idea papers is this nice one from 1997. And so here, as I said, you're going to try and solve the equations. So you want to get to the bottom of the loss function, which is the sum of the squares of the equations, including boundary conditions. And what the input is then is points in the domain of the PDE that you're trying to solve. And the output of the neural net basically serve as an ansatz, a trial solution for the differential equation that you're trying to solve. So, it's a particular form of an ansatz, the form where you nonlinearly build up the activations and so on in a way that depends, as usual, in a neural network on the weights and biases of the network. By the way, in this talk, we'll denote the weights and biases collectively as theta, the parameters of the neural net. Okay, and so you can set this up and descend this loss landscape aiming to solve the differential equation. And here, as in every such problem, the question of what optimizer to use enters. And there's classical PDEs, there's also quantum fields, and there's interesting works by Jim and others trying to use this kind of function space also as an interesting way to organize quantum fields, which we normally do in terms of Fourier modes. So both in the classical PDEs and maybe even in quantum fields, this is an interesting way to try and organize those problems. Okay, so it remains to be seen how well this approach will do when it comes to solving PDEs. Again, this is a beautiful subject with a long history, and for those who saw the spectacular results of LIGO, for example, part of that success was numerical general relativity integrating the equations of gravitational physics, which people did not need machine learning to do. It's done using another toolkit. But this is very tempting, and it's a very timely subject. You'll see a lot of works on it on the internet. Okay, so now I'm going to come to the origin story of this approach, just so in case it's of interest to those more on the machine learning side. So just briefly, our understanding of the early universe, which then evolved into what we see later times in cosmology, in the study of the history of the universe, there's a leading theory known as inflationary theory, in which the expansion of the universe was accelerating at a rapid rate. And that acceleration, according to the rules of gravity, where the curvature of space-time is related to energy sources, that expansion is driven by some energy source, which is most simply modeled as a potential energy function for one or more scalar fields. We'll call that V of phi. And so there's some such energy that's driving accelerated expansion of the universe at early times. And then, it's a non-trivial potential function that decays in some way and could be quite a bit richer than what I've drawn here, such that this accelerated expansion happened early on and then ended. There's a much weaker accelerated expansion going on in our universe these days. So this theory is a beautiful theory of the origin of structure, because this potential energy of the field model entails adding the field whose quantum fluctuations are irreducible according to the Heisenberg uncertainty principle. And they produce modes, quantum fluctuations, which in the context of the accelerated expansion stretch out and freeze out until they enter the observable patch of our universe later. And just from the fact that they have an irreducible uncertainty, that they have a variance, one gets fluctuations that seed structure in a way that gives predictions for what we should see at later times in the universe. And long story short, those predictions match up beautifully to observations. So this is a wonderful subject in itself. And it drives research in really trying to understand the dynamics of this process. This is a kind of crude model, and there's a lot of work on the dynamics of the process, which is sensitive to really very high energy physics. Okay, so this business of understanding what we can learn from what we observe in the universe is a very important and still timely subject. So the data that we get includes photons that we see from the time that atoms first formed, called the CMB, and also what we call large-scale structure of the universe, which is the pattern of matter in the universe, including observable galaxies and also the famous dark matter. And there's a beautiful data science problem, essentially combined, in collaboration with theory, to extract as much information as we can from these observations, which are growing in scope, decade to decade in a very rapid way. So just so you know, for those who haven't seen this, there's a great problem here to be solved that requires extracting information about the primordial universe from the data that you get from these observations, taking into account the fact that there's a lot of nonlinear evolution due to known physics in this picture. So, there's a standard approach to this, which has been, getting more and more precise. It's called the effective field theory large-scale structure. But there are also approaches based on machine learning that are extremely intriguing. And this is a partial list. And so just wanted to mention this as an action item in the field. Okay, but let me come back to the origin story for this algorithm that we're getting to. So there's this notion of early universe inflation, which fits the facts very well, but is not well constrained in terms of what the theory of it was in the early universe. There are basically two very distinct classes of dynamics that can produce this effect. One is called slow roll inflation, where you have a potential energy which is flat in a certain sense, where the physical evolution of this field on this potential is dominated by friction, just like in high school physics, where you have a inclined plane problem, and you can get in a regime where friction is important. There's a whole nother class of examples with very different predictions, where the field generates this accelerated expansion through a nearly constant potential energy, not because the potential is flat and because of friction, but instead because some interactions conspire to slow the field down. And a prototype for that is a relativistic motion with a speed limit that depends on where you are in this potential energy landscape, which is another option for the dynamics, which generates predictions for these tiny fluctuations that I mentioned, that in fact render the two distinguishable by actual empirical observations. And these are, observations that constrain what was going on nearly 14 billion years ago. It's a really amazing thing in modern science. What I'm getting to is that this dichotomy between slow roll friction dominated motion and these interacting versions of inflation where, as I said, there's some other reason that the field is slowing down and friction is not involved, suggests also a similar dichotomy in the world of optimization. Okay, so the analogy I'm trying to express here is that slow roll of friction is like gradient descent and its many descendants. And the other category is the thing we're going to pursue today. For now, just in the early universe context, these two are both viable. There are some constraints on their parameters. There's more to do there. And they're just they're distinct. Okay, that's the main statement here. So when it comes to optimization, where you're moving around on some potential landscape, we can now forget about this fancy inflationary early universe theory and gravitation and cosmology and so on, and just extract from this the following idea. So consider motion on the loss landscape as analogous to a physics problem, just as gradient descent is like friction-based, it's like adding a friction term to F equals ma. Here, instead, we'll consider motion on the loss landscape in a physics context in which the physics is relativistic, where the speed limit squared, the analog of the speed of light squared, is the loss function itself. Okay, so this formula is the action whose variation gives the equations of motion, whose variation gives the analog of F equals ma in this setting. One can work in a first order form where you have momenta and positions, or velocity and positions, velocity being theta dot here. And one can work out the consequences of this hypothesis, one of which is that there's being no friction, there's also a property that this physics model has, which is going to be important, which is conservation of energy. So the energy in this problem takes the form I've written here in terms of the velocity on parameter space theta dot and the loss v. And in the continuum model, and we'll enforce this also in the discrete model, this is constant. I'm stressing this partly because it's a distinction, but partly because it will give us more calculational control. And this is familiar to the physics side of the group, because such a conservation law is always comes along with useful consequences. For now, let me just say again what these equations are saying in words, which is that there's no friction. The particle flies around the potential landscape, the loss landscape, in a way that's determined by the equations of motion, the glorified F equals ma here, but without friction. So they're not slowed down, and the phase space is not contracting into local minima. Instead, it flies around until it finds a place where the loss is very, very small, at which point the speed limit forces it to slow and essentially stop. Okay, so that means that it has various properties that we can just prove. These are kind of trivial theorems. It can't stop at a local minimum, just can't, because the energy is conserved. The way it can get stuck is to get stuck in some orbit, and we'll treat that momentarily. It also can't overshoot v equals 0. And as we'll see, there's just a detail of the dynamics that makes it also faster in these shallow valley type regions that come up in machine learning. For now, also note there's very distinct from gradient descent. It's just a different category. And so we're motivated to really flesh out what its properties are. The energy conservation also gives us, I mentioned calculability before, and it gives us a handle on the behavior of the system, particularly in multiple runs. And this is grounded by computing the so-called phase space volume. So you ask in a classical mechanics model in general, you can ask for the volume in the space of positions and momenta, and little droplets of that are conserved. The volume is conserved. And in a situation with energy conservation, you can ask for what the phase space looks like in various regions of the potential combined with the momenta. And for later use, it'll be very important to note that this volume is very strongly dominated near v equals 0. Okay, so there's a formula for the volume of the phase space in some region of positions and momenta pi, with a delta function expressing the conservation of energy. It's possible to do the momentum part of this integral immediately, landing us on this formula, which, as you can see, is strong as v goes to 0. And we'll come back to this and write down a more explicit formula as a function of the Hessian and various minima based on this formula shortly. I noticed there's something in the chat. Let's see. How do you choose initial conditions, parameters for optimization? Could you accidentally choose something such that you can get stuck in a local minimum? So you can get stuck in orbit. You can also not have enough energy to get over a barrier, but you can easily add to that and avoid that problem. So you can't literally get stuck at a local minimum, because that would mean that you go to 0 velocity at a value of the potential that's lower than your starting point, and that would simply conflict with energy conservation exactly. But I mean, you're onto something in this question, because it's quite possible to get stuck in an orbit. So we're going to add something that keeps the system sufficiently strongly mixing chaotic that that doesn't happen, that the orbits are unstable. So
another question is, how can you stop at the global minimum at all? Because like if energy is conserved, then you usually have some kinetic energy left and you would overshoot and so on.
Yeah, that's the difference between, I mean, since Sven, you're a physics person, let me just say, is the difference between, it's the difference between pi and theta dot. So as you go, as you go toward v equals 0, theta dot absolutely must slow down enormously. So, you don't literally stop, but you're slowed down by the speed limit automatically. So pi is related to theta dot by a factor of E over V. So, in this formula, pi is getting very large, but theta dot is indeed getting very, very small. It's much like, for a Schwarzschild observer's point of view, dropping toward the horizon. It takes forever to get to the horizon. So in physics language, it's nothing more than that. And of course, any actual application in optimization is over a finite time, so you don't literally get to stop, but you get essentially stopped there, essentially stuck there.
Eva, can I ask
yeah,
a quick
please.
question too? So since you draw the analogy with inflation, in that case, the speed limit can in principle be controlled by a different function as the potential.
True.
So what happened in those cases?
No, that's a great question, Gary. So we played a little bit with putting a function of V in here. And it's on the agenda to do that more systematically and really figure out which, if you like, of these P of X models is the best, right, in this regard. So yeah, there's a yeah, it's a great question. This category of, energy conserving, the properties that we're stressing here of this example hold in, a wide variety of examples. There's what you're asking about, just putting some other thing here, which I agree with as a very interesting prospect. There's, inspired again by some inflation models, there's making it logarithmic instead of square root. But there's even just more simply, okay, making it a two derivative action, but take the mass to be 1 over the loss, and then, it slows down just because of that. It's getting very, very heavy. So the common theme here is the energy conservation, the prediction for the phase space volume, and such things, which would be true for all of these. And as you say, the question is, what's optimal among this class, and we don't know yet.
So there's a family of optimizer that you're proposing.
That's right. We call it, who knows what names will stick, but in the paper, we called this generally energy conserving descent, ECD. So we need to be more OCD about ECD to answer your question. Yeah, no, thanks. That's a good question. Any more discussion now? Because I'm happy to. Okay, so this measure formula that I just introduced is going to be particularly useful if the system has certain property as a physics problem of being strongly chaotic, which means another word for that is mixing, where after some hopefully small finite time, the definition of that property, which can easily happen in physical systems, is that the probability of finding the system in a certain region of phase space is proportional to the volume of that region of phase space. But to go back, in classical mechanics, in chaos theory, there's a lot of types of trajectories that can arise. There are periodic orbits in the system, and part of the question here, and as in regular classical mechanics, is how stable are those? So for example, the solar system is ultimately unstable, but with a ridiculously long time scale. But more generic problems have the property that orbits will be unstable and that trajectories that start out near each other will diverge. Okay, so in our context, the way that it can get stuck on a high portion of the loss landscape is not literally by stopping, but by just getting in some orbit where it stays high on the potential. That's not expected to be very generic because of, it requires symmetries, but in any case, it does happen in some experiments where, we see that it's stuck in orbit. We can track that that's what's going on with the parameters. But it's very easy, since the more chaotic dynamics is the more generic thing. If you add some features to get the trajectory to diverge, and I'll be very explicit about that shortly, you can see that that does unstick it. Okay, just a little more context. This kind of thing arises in physics in another way. I mentioned the solar system, but galactic dynamics involves a rich set of different types of orbits, so inspired by that, and also by mathematical studies of chaos, particularly billiards problems where you can prove strong forms of chaos and mixing. We're going to add some elements, basically analogous to billiard ball bounces, that essentially guarantee that the trajectories mix, that nearby trajectories diverge in a finite time, in a small time. And the idea here is, again, to ensure that the system is in a chaotic mixing regime where the orbits look kind of, like these blue ones. The idea, again, is that nearby trajectories are going to separate, and the way that works in mathematical billiards problems is very visceral. To rays that hit some billiard ball will come bouncing off in a very different direction. And once you have this property of strong mixing, the statement is that the probability to find the droplet in some region of phase space is proportional to that region, the volume of that region of phase space. And this is a stronger condition than mere what's called ergodicity, which is a thing about time average, not at late times, not phase space volume average. Okay, so just for fun, this is quite silly, but here's a mixing problem. Milk and coffee, and you see it's a very quick process there. Okay. We are experimentalists. Okay, so here's the, after all that ado, here's the algorithm. It's based on a discretization of the dynamics I mentioned, basically taking the equations F equals ma, but relativistic with the speed limit square being the loss, discretizing that. Here I've written it in a first order form that's very analogous to the way you'll see, gradient descent with momentum, update rules written with the positions and the momenta. But you see that these formulas are infected by this direct dependence on the loss, as well as a force from the gradient. So the thing that there's still something that's forcing it toward where you want to go. And finally, the energy conserving equation. We enforce the energy conservation, even though a discretized such system will generally start to lose that. We reinstate it in the algorithm. To the previous question, which was a great question. Well, basically the question was, can you get stuck, not stuck sitting at a high local minimum, but could you say get stuck in a basin of a high local minimum? If you find that happening, you can always increase the initial energy and fly over barriers. Regarding the chaotic dynamics, inspired by those billiards problems, we introduce, it's definitely if there's not enough progress indicating getting into such a high orbit, we simply bounce the system. So randomly rotate the momenta, inspired by the billiards problems. One can of course do this in gradient descent with momentum as well. It's just that there one doesn't have the energy conservation to lead to the prediction about phase space volumes and such. So it's of limited use, although one could try it there. And these bounces can be inserted in various ways, either or not enough progress, or just even toward the beginning to get it going in a chaotic manner. Okay, so that's the basic algorithm. Let me unpack this measure formula a little more. So as we go toward low V, low loss, that formula that I had written earlier for the measure of a given region on phase space, let's apply it near small v, small, near some local minimum. Okay, so, and here all I've done is take the approximation that we're well below the initial energy. Okay, so there's, some local minimum with a quadratic Taylor expansion around it, with the masses being mass eigenvalues being this square being m squared here. So one can easily plug that into this formula and get it in a form where now we only have the kind of overall direction radially away from the minimum. And here is the dimensionality of the parameter space. And again, these m's are defined here. And v is as defined here, is the value of the loss at the local minimum that we're looking at. Okay, so what we see is the volume of phase space in such a region gets larger logarithmically with v, and in a power law with how flat the minimum is. So this prefers flatter minima, and also prefers the low loss region of phase space. Okay, so this is a concrete formula. It's our ability to just compute this prediction depends on the energy conservation. As a physicist, will be well aware, and if anybody else is interested and wants more, I can explain more about that. It was just to maybe do that shortly. As part where it entered into the calculation was here in imposing the delta function of energy conservation. Okay, so we can ask just in some, admittedly, very small scale thing, just to check ourselves on this. Here's a potential with two minima, different Hessians, different V's, and we do a small sample of trajectories. Do they agree with this formula? Well, yes, within 10%, on this small statistics sample. So okay, that should work, and it's working at the level it should for this little exercise. For PDEs, we set up a bunch of tests where we make it difficult, at least in the sense that sort of standard solvers you plug this into fail, without much tweaking and so on. And we ask the neural net to try and solve it. This is a problem which we set up where we know one answer. There's also another answer, another solution. We set it up so that the answer. Okay, we set up a kind of Poisson sort of problem. It's nonlinear. There's a function f here on the right-hand side. That's some highly oscillatory thing that we set up to give us an equation for which this oscillatory thing is a solution. There's also a second solution, and the algorithm over hundreds of trials will find both solutions as it should. So this is testing both that the optimizer can solve, again, relatively small scale, but a non-trivial PDE problem, and that it can find multiple solutions. Okay, so I already mentioned this, but and this is something I'd love to discuss. There's some. Oh, please, yeah.
Question on this on the previous slide.
Yes.
So with PDE solutions, often, right, we don't know that or we know maybe about the existence of a solution, but we don't know whether we are actually converging towards an actual solution. Is there somewhat a guarantee here, or that's a path towards a guarantee that you can see?
Yeah, so it is conditional on the mixing time being shorter than the time of the experiments that you're doing. It also depends, the formula depends on the Hessian at the various minima. But with those, so if the loss function, being the sum of squares of the equations, doesn't have any giant hierarchies in the Hessians, and also given that the billiard intuition strongly suggests that the mix is happening, and we see this in these experiments, I think there's a strong theoretical reason to expect it to find the multiple minima. But what I've said just now, first of all, it has some conditions, and secondly, it's not a mathematical proof, right? I mean, in mathematical billiards, there's many proofs. They're not all, there's proofs that go up in dimensionality. There's proof, so the intuition that chaos is typical and that this kind of bouncing induces it fits all the facts that are known, but even in the mathematical problem, it's not that there's a proof for every situation. So we certainly don't have a proof for every situation here. But there's, I think these are reasonably weak assumptions. The assumption that there's a small mixing time, and then what you get is a prediction depending on the flatness or not of the degenerate minima. So
the chaos part is to ensure that no matter what initial conditions you start with, you can always get to a basin where the potential has large phase space that dominate.
Yeah, exactly. That's the idea. That's right. And here in this and here we're kind of beginning the tests of that, and it's working so far. So one thing people talk about in machine learning from what I've seen, and I'm not sure, what things are lore and so on, but there's some argument that flatter minima are better in some way. Sort of the idea is you make less of a mistake if you just shift it a little bit. So for what it's worth, our formula predicts finding, the flatter minima since they have greater phase space volume. Also, if you just look at what's going on there in a shallow region and just look at the dynamics of the two cases, so friction dominated motion, you can solve that, and well, in a shallow valley with the mass going to zero, the behavior of the particle on that shallow part of the landscape, is easily solved. It gives you theta goes like, exponential of minus m squared t over the friction f. And in BI, it's speed limit dominated. So the value of theta dot magnitude is, square root of the loss. And that's also solvable if it's, rolling in that direction, and gives something exponential in m times t. So again, exponential minus something times t, but here, it's since we're interested in a shallow valley where this m is going towards zero, the gradient descent version of this formula, depending on m squared up there, is moving much more slowly toward the minimum than is BI. Okay, so, or anything that would have the same feature of a speed limit. Okay, so for these reasons, it seems like it should play well with at least some of the lore in machine learning about there being these valleys and about the flat minima. Well, here's another fun small scale problem, a 10-dimensional Zakharov function with a small valley. And we find something with a shallow valley. In all these experiments, we hyper optimize both gradient descent with momentum and BI in what we think is a fair way. And in doing that, in this kind of shallow valley sort of problem, we did find an advantage in this kind of small scale synthetic test function arena. Okay, so that is an experiment that is testing this kind of setup, this kind of idea. I mean, the theoretical result to do with shallow regions. So, okay, so here's the kind of general, here's a table of the differences. The way that gradient descent gets to a nice minimum is through its stochastic behavior, letting it sample, letting it go around and find different parts of the landscape. And at the same time, the phase space is contracting. So it kind of finds, if you get the right balance between those two things, it finds a nice minimum through a combination of the friction and the stochastic evolution. But it can stop in a high local minimum, whereas there's a theorem that ECD simply can't. Similarly, the overshooting. The gradient descent has a nice feature of depending only on the gradient, whereas we have this explicit dependence on V. We said the thing about the shallow regions. We get an analytic prediction for the distribution of results, whereas here it's kind of a little bit messier stochastic sort of understanding of that. And there's a lot of interesting works on the role of the stochastic noise in gradient descent. But it seems to me fair to say it's a bit cleaner over here to just have this prediction. Of course, on this side, we need to ask, well, does noise from mini batches or other sources, screw with these results? And that we'll see is working out okay for a good theoretical reason. But let me come back to experiments on the basic properties. So we already talked about little experiments on the shallow regions. Let's do a study of a highly non-convex example. We have several of those at the same scale. So here's one that we can visualize very well. The Ackley function, here's its form, here's its picture. And again, we do a fair hyperoptimization for the two and find that, BI or bouncing BI, BBI behaves as predicted. It goes around, it takes a while to get there, but it settles in the global minimum. Whereas gradient descent with momentum either either just kind of settles in a local minimum, or if we do a sort of catapult-like thing, it can get out, but then it just is erratic later. Now, to be clear, we're not giving every optimizer all the modern tweaks that they can enjoy, but we're trying to do kind of a head-to-head comparison here. So at this level with a fixed learning rate, hyper-optimizing that and the momentum, and for BI, hyper-optimizing the learning rate, these are the results, and it makes sense from the theory. The Rasmussen function is another such thing which we can scale up in dimensionality, and we find similar results there in comparing gradient descent with momentum and BBI. Okay, 400 dimensions, similar. So we can do the high dimensional case in this sense. So what about the noise? Well, in our framework, we can think about the noise. I mean, the noise appears through the presence of different samples of the data every step or every n steps or something. And for us, that's understandable as an explicitly time-dependent potential, because of those jumping around in steps, jumping around the batches as a function of time because it's a function of steps. So the physicists would say, okay, given this, now energy conservation is going to break, and that would be true of a physical model. But here we just use our power as engineers in this context to nonetheless impose energy conservation based on the original energy. So we just get the same results. Because of that, it can't stop at high local minimum, and it will slow dramatically near the global minimum. So we, just long story short, in the presence of batches, many batches, we also maintain the energy conservation by hand. Okay, so it's interesting to ask about what happens to the stochastic noise introduced by many batches in our context and compare that to SGD. So there's a lot of interesting works on this, worrying about how to take a careful continuum limit or also just being conservative in a certain sense and just working directly with the discrete version, where one can work out, for example, fluctuation dissipation relations that occur, that happen averaged over many batches, averaged over trajectories. So let me see if I'll get to the sort of punchline of this in the next slide. We can, follow these methods, just generalizing them to our case, and get such relationships. In the continuum limit, if we're careful about it, we find a certain formula that can be contrasted with the one for SGD, where of course there's a kind of friction term. In our case, there's not. There's this more elaborate term where you might have expected a friction term. And we take into account the what happens at the different batches with the jumping around of the data input. So okay, you see the difference. And here's a attempt to kind of summarize the point of that. These formulas get complicated very quickly, but there's a sense in which SGD with momentum is a glorified sort of Brownian motion, maybe with some anomalous exponent here, but basically it's giving the familiar sort of diffusion on the space, on the parameter space, where you get formulas, for example, like d of the variance squared, the variance of theta dt is proportional to the variance of the velocity. So we have a contribution like that, but for us, the point is the speed limit limits the variance of the velocity. So you know, that is a direct contrast between the two. And what it means is BI is not spreading out as much just due to stochastics. It's a bit more, you know, deterministic. But the way it explores is through this other mechanism of the chaotic dynamics and so on. Okay. Now we can ask, okay, what is this doing on the very basic, somewhat old-fashioned benchmarks for machine learning? And, you know, okay, it works for CFAR and it works for MNIST. And that's saying that it's not failing to generalize and saying that it's able to deal with noise. So this is, again, you know, small statistics. We're kind of resource limited so far. Now let me say a few things about generalization. So you might naively expect this to overfit if you just take the words I said very literally, and this is related to Sven's question earlier. You might have expected that, okay, if it just flies around and then only, you know, suddenly stops at v = 0, that would be bad because it would overfit. In fact, you know, it does stall before that. And both, you know, the MNIST and CFAR, as well as these PDE examples we're doing, you know, illustrate that, they check that. It would be nice to, you know, quantify that distinction a little bit more, but in fact, you know, this kind of argument would be too naive, and it's just that, you know, it does kind of slow down dramatically and sort of stall, again, like a Schwarzschild observer outside a black hole, watching something fall in. It doesn't literally get to the horizon. So that's, you know, the status of these very basic benchmarks. Now, of course, we need to do more. We need to do more general experiments, and those are in progress. We're trying to do those while getting enough resources to really make them possible. And, you know, also at a theoretical level, problems that require feature learning are clearly the most interesting. So here, you know, we're trying to get into such experiments. You know, recommendations for that would be appreciated. We are thinking about the theory of that. So there's a lot of interesting work on representation learning. And one thing that we can observe, again, at what I hope is a nice, simple, you know, level of kind of getting to the point, there are long calculations one can do on this problem of whether or not, say at large width, the thing is we're reverting to a linear model, just updating the last layer, the linear layer, or if it's really learning a representation by updating the parameters throughout the neural network. Okay, so we can ask, let's compare our situation to in a setup where SGD, say in some sort of NTK limit, would not learn representations. Will ECD or BI do so? And, you know, tentatively it seems yes, just because, I mean, one reason for that is that the chaos, which may be generic or may be induced by, in any case, by the balancings, that takes updates in the, you know, more boring linear layer into updates in the more interesting layers. Now that in itself isn't, you know, learning something from the data, but it gets it moving in a direction where it can do so. And so it gets it finding those regions of phase space where it's been established, as far as I know, that there can be representation learning even at large width. So our tentative understanding is that this has the capacity to feature learn even at large width. And so we want to pursue that both more theoretically and experimentally. Okay, I think there's an application in the extra dimensions of string theory that, well, a number of our hosts have.
Just real quick, you've got about 5 minutes left.
Yeah, so I'm not going to belabor this. If anybody wants to talk about it, PDEs arise in many contexts in science, including in string theory, and there's a number of experts in the group on that. So let me not go there. but just summarize so we can have more discussion. So I introduced this class of optimization algorithms that is very distinct from anything friction-based like gradient descent. It has favorable properties that we can prove. We have yet to really exhibit them in full-scale machine learning applications or full-scale scientific ones. And that's what we want to do next, along with further development of the theory. So the energy conservation enables more calculability, more predictivity. And so we're hopeful that this can be exploited and that the algorithm can be useful. And so I'd love to hear about possible any discussion, including ideas for particularly suitable applications that any of you might have. So thank you.
All right, thanks a lot. Eva, that was a wonderful talk. I'm sure there will be a number of questions. If you have a question for Eva, please just feel free to unmute yourself and ask. Maybe in that case, while they're coming in, I'll ask real quick. So in this, you made this point about Born-Feld optimization in the infinite width limit and how it's, of course, going to be different from gradient descent, and therefore some of the feature learning conclusions about the NTK should not be expected to hold. Could you say a little bit more about what you guys are doing and what you're finding so far?
Yeah, I mean, it's a great question. Part of what I'm doing is trying to answer this question you've asked me before. So, but I like the question a lot. As you know, one can simply write down the equations for the updates of the various layers of the various pre-activations in the different layers. And there's very nice treatments of that in the literature, including in the book by Roberts and Yaida. There's also a scheme for initializing differently so that you essentially force the system to update the hidden layers. And it seems to us, so we can write down these equations and start to analyze them. Let me say two things though that are kind of more bigger picture obvious. One is I'll come back to what I was saying here, but before that, so obviously if BI gets to the same place as gradient descent through whatever route, it would have the same consequence, that it wouldn't learn any features. So from that point of view, the question is, independently of the intermediate trajectory, does it go to the different places or not? Say, does it go to the solutions where you would learn a representation instead of just the one that NTK would find? Now, a priori, you'd say, oh, yeah, the measure formula is predicting that it will, and that sounds good. But the one thing to be careful about in jumping to that conclusion would be, okay, there are these feature learning regions, but if they are super far away in some, in the appropriate sense, you might not get there in finite time, right? But here, what I'm saying is, then in essence, the chaos of the system here will bounce it around so that, it'll, if it was moving in some linear, non-feature learning direction in parameter space, it'll get kicked to have an update that's substantial in the feature learning directions. So in some sense, it's like the bouncing or chaos is introducing a little bit, an analog of just making different initialization choices. We need to think about this more, but this is my current understanding of what to expect. So, and there's some interesting discussion and debate in the community about this, but I think this will be the point. Does that help, or was that still unclear?
A little bit. No, some of the things you said definitely helped me understand a little more. It's actually an apt time to advertise that the Dan Show team together and separately Greg Yang are both giving Physics Meets ML talks in the next 6 weeks. So, for people interested in what Eva was just saying, some of the experts in this story about feature learning and infinite width limits and parameterization and criticality and so forth are all going to speak in the next 6 weeks. So that'll be fun. No, that's helpful, Eva. Thanks a lot. Are there other questions?
What applications in large scale structure you have in mind?
Well, any problem that you want to apply machine learning to, with optimization, you could substitute in this optimizer, right? When it comes to, so, in that sense, it's just kind of a global, so I guess in any problems, including large scale structure, part of the question would be, is this a problem where you really want to make sure you're finding the different possible solutions, which would be an advantage of substituting in this sort of optimizer. More generally with large scale structure, I'm very interested in whether it can, machine learning can, in a reliable way, figure out a better function space to use, than the usual laborious Fourier expansion up to K nonlinear. I think there are many ways people are using machine learning in large scale structure, and you're an expert as well. But one question I was asking Jim is whether or not the reformulation of quantum field theory as a, in terms of machine learning functions, neural net functions, could play well with the EFT of large scale structure. Could one substitute that for the usual Fourier expansion and get similarly reliable results, but learn a better, function space to capture, the short scale stuff, the baryon physics, or even the nuisance parameters or something. Of course, people would scream that it better be interpretable, better be, reliable. And I don't, that would always be the main question to ask, but.
Okay, thank you.
Yeah, thanks for the question.
Yeah, so you're saying by using something other than the Fourier basis, it might be good for certain features of large scale structure.
Well, it would have the capacity potentially to learn a basis that would capture the short scale stuff in a way that's that legitimately gives you fewer counter terms, fewer of these bias parameters. But I really don't know. I mean, there's interesting work by you and by Miranda and company, and people doing field theory in some way using neural net functions instead of the usual basis. And I'm not saying much except raising this.
No, it's a fascinating question. It makes me realize I need to learn more about large scale structure effective theories.
That would be half the point of it, is to have an excuse to really learn.
Dig in, yeah. I do have one more question on your talk, if you don't mind. So you mentioned that part of your point is that due to this exponential decay, BI is going to be better at exploring flat potentials than or nearly flat potentials than SGD is, because of these relative factors of M. And you've also emphasized this point about PDEs, and of course we have some cases that we love where we have families of solutions to PDEs that are continuous, where we have moduli spaces rather than isolated solutions. Have you thought much about using BI to explore moduli spaces of solutions? It can't literally be doing it because you can't be on the completely flat part, because then it really won't update. But I was wondering if you've thought about putting those together, the PDE idea together with the exploring flat directions.
Well, actually, it won't update if it's at 0 and flat. I think that's a very interesting question. Although, just to be totally frank with you, I'm probably the least enamored of moduli spaces of anyone in the physics community, because I find they are non-generic, and I think I'm more interested in more generic landscape, including in compactifications, where the rigidity of generic spaces seems to me to be the lesson or the dominant behavior. So I find moduli spaces to be interesting, but extraordinarily special, and so
Sure.
that's my honest reaction. But the spirit of your question is perfectly apt. It indeed would tend to favor that. I mean, that would be like the extreme thing it favors in some sense. So that's a very reasonable comment.
I mean, BI would be better at it than SGDs, I guess the point, right?
Yeah, that sounds right. And it's a great suggestion. But yeah, I would like to understand better to what extent, coming back to the ML side, to what extent the lore about flatter minima being advantageous, to what extent that's really right. Does anyone here have an opinion on that?
No, but I have a different question. Wait.
Maybe give it like 10 seconds, Sven, to see if anyone wants to chime in on that point and then ask. Flatter minima. All right, go ahead, Sven.
Yeah, so you show that you kind of find this, region of phase space where, which is dominating, right, in terms of the global minimum. My question is in terms of time scales. Can you estimate when you are guaranteed to find it, or, is there somehow an intuition behind when you find it, in particular, how that scales with the number of parameters when you go to larger nets or when you go to larger problems? So, I mean, how it scales effectively with the canonical parameters?
Yeah, I think that's a fantastic question. It's very much related to predicting the mixing time in chaotic dynamics as a function of dimensionality. And this is something we would like to do more of and learn more of. If you look at just forgetting about this application, but look at people doing that in other parts of physics, right, like in galactic dynamics or in which of course is in 3+1 dimensions, but there's a lot of kind of general expectation about chaotic dynamics dominating and so on. But at the end of the day, in a given problem, it's usually hard to actually compute and treat every case, and so there's a lot. It is an experimental thing, even in but so from that point of view, again, even in mathematical, so mathematicians have done brilliant proofs, going back to Sinai billiards and so on, of these things. The proofs involve, I mean, they basically confirm the basic intuition that you have this these diverging trajectories. But again, they have to treat the special case where you hit some corner and blah blah blah. So I guess my personal, there's probably more to say about your question. It's a very interesting question. It would be obviously good to achieve more absolute guarantees, but my feeling is that the lore about chaotic dynamics being generic and the mixing time being able to be very fast seems to be pretty robust, just as a matter of fact. I mean, how it is. You can vary parameters. There's some islands of stability, blah blah blah. But those really are there really are big open sets where strong chaotic effects are expected. But yeah, sorry, I'm going on a bit, but I think your specific point about thinking about that in the context of increasing the dimensionality is a great question, and I'll probably think a little bit more about that specifically. Obviously, most of the applications in real life are not going up in dimension and in terms of the space-time dimension, but they are in terms of, there's also plenty of work in condensed matter physics also about, high dimensional spaces for many bodies situations. So there's no doubt more wisdom out there and more to do. So
Yeah, no, that's very interesting. I mean, my thing was in terms of, machine learning. If we would like to have an estimate how long we want to train them, and
Yes.
also because there's some cost associated with it, right? If you can say, okay, these larger models or so, at some point actually it becomes easier to find these kind of regions, for instance. I mean, they might actually be easier to train than other models, and these will be super interesting statements, right? If one can make
Yeah,
something
yeah.
like
Thanks,
that.
thanks a lot. And that's a good thing to press on.
There's a question from Moritz.
Yeah, hi Eva. Thanks a
Hi,
lot for the
Moritz.
talk. That's super interesting. There's one thing maybe I'm a bit confused about. So it doesn't matter in your optimizer, right? That the minimum must be at v equals 0. So it doesn't matter that the loss can train to 0. Is that right?
Well, yeah, I probably should have added more on this, even though I mentioned it. So we can add another hyperparameter delta v if we wish, and add it and reduce it until you get kind of optimal results. By the way, you can use such a parameter to give yourself early stopping in a controlled way if you wish. Now, but it so so happens.
So you do put like a generic problem. You do not know a priori like what the magnitude of the global minimum is. It's not in general 0, right? Unless your network can train the data perfectly.
Absolutely, you don't know that. It may be though that it's often close. We are doing more bigger scale experiments on traditional benchmarks to see how that goes. But be that as it may, in CFAR and MNIST, this was a non-issue, even with generalization, and so. Yeah, the fact
that but so then like if you don't go to 0, like if you're say in an MNIST example, your neural network wouldn't be large enough to fit it to 0% error, then it doesn't matter what the energy is of your optimizer, right? If your energy is too high with respect to the global minimum, then you can run endlessly and never end up anywhere, right? So my question is if the choice of the energy is really so innocent. You made it sound like if you just get stuck somewhere, just raise the energy, and then you will finally just raise the energy until you find the global minimum. That's what I got from your talk. And I was wondering whether this statement, whether this is really such an innocent choice, in particular since the global loss.
Sorry, there are two things. There are two things that we shouldn't confuse. What I was calling delta V is if as needed, one can play with the absolute value of where you're essentially adding to constant to the loss V. That is different from what I was calling adding energy at the beginning. What I was calling adding energy at the beginning was starting with more from physics.
No, I understand that these are two different things, but you do it doesn't matter. The absolute energy doesn't it doesn't matter. Like they are in relation to each other. They change. They change the fact whether you will ever find the minimum, right? That I misunderstand. If you give it a lot of energy, kinetic energy in the beginning, so the thing moves quickly, and you're and then it goes somewhere near goes very near to the global minimum, but then the field slows down, but it doesn't slow down to 0 because V is not 0 at the minimum. I'm wondering whether the optimizer will just go off at somewhere else and never hit the global minimum. Yeah, and never slow down enough.
Right. No, I totally appreciate this question. It's definitely fair to say a priori it's not known. For PD, I mean, PDEs are a case where the thing you're trying to get is 0. So that's an example where you do know. Yeah. You might not know that there exists a solution, but you know that the right thing to aim for is V equals 0. So yeah, and you're saying, okay, fine, if you add like momentum toward the beginning, does that also have the implication of making it that much less able to stall even at a split non-zero V? I mean, it's a question of what terms dominate two very different regimes. I honestly need to look a little more at it, but I think that in general, it's a fair question. In practice, it hasn't bit us yet, and we'd like to understand, why that is. Maybe you already have understood why CFAR 10 is too dumb to see this
Well, you
problem.
can try. It depends. What matters here is how large how many parameters you fit to the problem, right? That if your neural network has 1 million parameters, you get 0% training error on CFAR, I guess. You could achieve it in principle.
Yeah, you could, but you also want to generalize. So I'm saying that both, you do generalize, so you're not getting bit by either not being able to get to v equals 0 or by being able to but overfitting. So but yeah, but in general, we totally agree that this delta v is something to it's a although there are some favorable properties, this is definitely an extra piece of work to understand it in a given problem. But so far, I'm just saying that the nominal goal in PDEs or even I mean in many problems is small say MSE loss. It may be that the data just doesn't let you get there, or the net parameterization doesn't let you get there, but it's kind of not, it's not like the worst first guess. And then what we need to do is understand what in case maybe the thing we should do is set up a case where we know the net doesn't know that it's a bad approximation, and then use this delta v to tune ourselves down to where it needs to go. So yeah, I mean, this is definitely on the to-do list yeah, we just haven't been forced to it yet because these benchmarks worked, but and PDEs are always available. So I must say I'm just not sure how, I mean, it's an obvious question. I'm not sure how big an issue it is, but anyway.
Can I actually ask a question directly related to this? Because Moritz, you more or less asked the question that was the last one I wanted to ask. I wanted to ask it in a slightly different way though. So certainly in the PDE case, indeed, the global minimum is at v is 0 because it's a sum of squares. And in that case, because I'm just interested in finding solutions a priori, I'm not worried about generalization or these things that we would normally talk about in machine learning. I just want a solution. So what in this context of cranking up E to help you get out of local minima basins, like you were mentioning, in the case of SGD, I wouldn't just keep cranking up E because I'm going to have an overshoot problem or something like that. But in this case where you hit the global minimum, it seems like it's just going to slow down. Why can't I just keep cranking up E? I mean, I can't have a free lunch, I guess. What's the issue with cranking up E?
Well, I suppose the main issue would be that so also let me back up. So in these, highly non-convex things, you can easily get yourself, you can choose to be in a place where you have that problem and you need to crank up E. In the benchmark problems or the PDEs, that hasn't been our issue, just FYI, okay. For whatever reason to do with the shape of the things. I guess just on very basic intuition that the downside of increasing what we call delta n, the starting with more momentum, is maybe it'll just take that much longer to get forced down to where you want to go. I mean, I mean, on the face of it, it's not a problem. It's an option. It also goes in a good direction in the sense that in a general physical system, the higher energy you are, the more chaotic you expect things to be. I don't know if that's the case for the landscapes we get in ML so much, but it's the generic physical intuition, so it has that going for it. But yeah, maybe it just kind of makes maybe there's a downside in it making it then take longer to actually settle on the global minimum.
So as you're descending the basin, it might take more orbits around the basin as it descends down or something like that.
Yeah, maybe something like that. It just maybe it takes longer for the gradient to push it in a way that's actually learning, right? I mean, but it's a great question. Yeah, I don't mean to minimize any of the. I mean, these questions are important, and just
Eva, I think it's a real gain that, because part of your point that you're emphasizing, and Moritz clarified it by asking about whether the global minimum is really at V, because when the global minimum is at V, you're going to slow down and you're going to stop there and you cannot overshoot, right? I mean, the naive issue that I would have thought with raising E is that you're just going to overshoot in the SGD case, but you don't have that issue here. So it seems like, to me, I'd be really curious to know, is there a fundamental issue with raising E in that case, given that you won't overshoot a global minimum at V equals 0.
Yeah, I think that is a great question. Yeah, no, I think you and Moritz are both asking, important questions. And I think they're different. There are these two things, there's delta N and there's delta V. And absolutely what you're saying about SGD with momentum is that if you put too much momentum, you just, you're not contracting, you're not letting the friction contract the phase space to stop where you want to stop. So that is the difference, absolutely. So yeah, is there a downside to increasing delta N just enormously? Great question. And certainly, as Moritz is stressing, we've gotten away without really needing this delta V, but what is really the general status of that beyond PDEs?
Maybe there's a compromise between the volume of the phase space and the momentum at which you assess the phase space. So the time you spend in that region is small if your momentum is large. So if you increase your energy too much, then there's a big region, but then you don't get to sample that region in a big enough.
Much time there. Yeah, I see.
Right.
Oh, very good.
Can I ask one quick last thing? So you went super fast over the CFAR example. So I just wanted to check. So you get similar accuracy to other optimizers, and are you faster in the CFAR example than gradient descent with momentum? 1,000 epochs looks sort of normal, I guess, right? So I want,
yeah, no, I mean, we're not seeing any particular advantage here. We just get the same sort of thing with the same. If we compare apples to apples, we get the same sort of results for CFAR. Now, others have stressed that, and I'm very sympathetic to this point of view, that although these are kind of traditional old at least previous benchmarks, they're kind of boring in that. I mean, from what I gather, like, you don't even have to feature learn to solve them and so on. So we are, interested in going to problems where you really want to find the more interesting solutions, if that makes sense. So, but yeah, just to be clear, I did go too fast probably. This is just, as I said here, just a check of basic competence. It's not, it's not an advantage at these scales.
Yeah, but it's cool to see that it works similarly to the normal optimizers. I think it's really super interesting for PDEs in particular, and I'm wondering now whether in cosmology we have like the suitable PDE to try this. You can do large scale structure of PDEs, not the way it's usually done, right? Usually you do not large scale structure with n-body simulations, so it's not directly a PDE solver, but normally PDE solvers are done on smaller scales, right, where you have hydrodynamic stuff for a galaxy or so. So it's not so much something we are working on so much about. So Gary and I are also very much into this business of reconstructing the initial conditions of various machine learning methods. So yeah, it's maybe there's a PDE in cosmology where it could be useful. Anyway,
that'd be fantastic. We'd love to collaborate on such things because both because there's a hope here, kind of reasonably motivated hope for an advantage, but also just because it's fun to work on different things. So it's good to hear. No, I understand. I mean, yeah, you're doing great stuff on that. And yeah, like you say, there are many ways, there are many parts of the large scale structure problem, right? And so
there are many people, many parts to it. There's certainly still like I think we're still in a really early stage of that. I think in 10 years this will look amazingly much better. This business. Yeah, that's super interesting. Thanks a lot.
Yeah, thank you. Thanks a lot, Moritz.
All right. That was a ton of questions because there was a lot of interest. Eva, thank you for the wonderful talk. For everyone that's still here, which is a good number of you, sorry to go so far over, but hopefully you loved this discussion. Eva, that was great. And indeed, I guess I'm also advertising to you. We're going to hear from Dan and Show next month, and we're going to hear from Greg Yang next week. So, right in this area that you're talking about, it might be relevant. So thank you so much, and looking forward to seeing more from your group. And thanks to Bruno too. I see you in the audience.
Thanks to all of you. This was great fun.
Thank you.
Thank you. Bye.